Hi everyone, welcome back to Chem Help ASAP. If you have ever wondered why table salt dissolves in water, you are watching the right video. Let's take a look at ion-dipole interactions. As usual, we will start with a definition for our ion-dipole intermolecular force. So this is an attractive or repulsive force that forms between an ion and a polar molecule. The key here being it must be a polar molecule. It must have a permanent dipole. So I mentioned table salt dissolving in water. And when table salt dissolves, it becomes a cation and an anion, specifically a sodium cation and a chlorine anion. And the reason why this forms is because water comes around and stabilizes these ions. So let's take a look at the cation, the sodium cation specifically. Sodium has a positive charge. Water, of course, is a polar molecule. It has a permanent dipole moment, which points towards the oxygen. So in essence, you have a partial negative charge on the oxygen and partial positive charges on the hydrogen. So what's going to happen is you'll have the oxygens of water lining up with that sodium cation to increase those negative positive interactions. So if you take a look at my picture over on the right, if this purple sphere represents our sodium cation, then you can see the water molecules ranged around it such that you get these positive, negative, attractive forces set up. And of course, I've represented this in 2D space, but what actually happens is these water molecules completely surround that sodium cation. And what you form are called spheres of hydration. The same thing happens with the chlorine anion. So if I come back over here to the left side of my page, chlorine, of course, being an anion, has a negative charge, so the water molecules are going to orient a little different around it. You are going to have the hydrogen atoms with their partial positive charge to set up an attractive force between the chlorine negative charge and the hydrogen partial positive charge. So I have a 3D representation of this over to the right. We'll call this green sphere my chlorine anion. And this time the water molecules are oriented so that the hydrogen with its partial positive charge is oriented towards the negatively charged chlorine atom. Again, this does not show the entire sphere of hydration, but the water molecules completely surround and stabilize this chlorine anion. This is what makes table salt especially so soluble in water. Now, having ions in water is really the classic example, and it's the one that most people are used to in their everyday life. But it does not just have to be water that acts as a stabilizer for these cations and anions. We can take table salt and dissolve it in another solvent like methanol. Table salt will still form its anions, but in this case, instead of being stabilized by water molecules, it's actually stabilized by the methanol. So again, if you look at my 3D models on the right, you can see for the sodium cation, we have the partial negative charge on the oxygen stabilizing this cation. And again, instead of forming a sphere of hydration, this is going to form a sphere of solvation. The same thing happens with the chlorine anion. So we have the methanol this time. Again, the hydrogen from that oxygen-hydrogen bond stabilizes the negative charge on the chlorine anion. Again, this also forms a sphere of solvation and stabilizes the ion. Remember that these spheres of hydration or spheres of solvation are fluid. They are not fixed crystalline structures. Instead, they're constantly moving and breaking apart and reforming. I hope you found this video helpful, and thanks so much for watching.